Alright guys, welcome to the shop here. Figured I'd make a little video talking through some of the design principles that I worked through on the development of this removable tool setter mount that I built for the X7 here. There's a lot of companies that make this stuff, and I'm not claiming to reinvent the wheel or anything. I found value in it as a design exercise as well as a manufacturing one. So I thought it would be a fun challenge to see if I could make something to suit this need here. Titans of CNC came out with a video a little while back for their X7, developing their own removable mount. Reason being is when you have a machine with limited X travel, like X7 behind me only has around 16 inches of X travel, which isn't a whole lot. And when you want to fit, in my case, I have two 6-inch vices as well as a fourth axis that I'm shoehorning into that space, and I want to have some flexibility. The tool setter is almost always in the way, and it makes sense to have the ability to remove it from the table when it's not needed, and to get it out of the way of larger pieces of work and different setups that you might be doing. So that was the main motivation for it. Something I've been kind of thinking about for a little while, but seeing their video got the juices flowing and inspired me to commit and get like at least a working prototype fleshed out and machined. So here's the model of it. Nothing earth-shattering. It consists of the tool setter itself, an upper half and a lower half. This lower half lives on the table. It's drilled in counterboard for an M12, so that gets bolted to the table and lives there forever. The upper half is bolted to the tool setter, and ideally you can remove and replace this thing with a high level of repeatability on the stylus. So there's three main differences with kind of comparing their design to mine. There was three main differences. One was the mounting mechanism kind of design and arrangement. The second was the addition of this, I guess this is more of like a packaging thing, but housing everything inside of a pocket to keep coolant and chips off of it. And then the third consideration was overall height, which we'll talk through in a little bit. Before I get too far into the first design point, the mounting mechanism, I'll bring up is this practicalprecision.com. If you do a Google search for Maxwell Criterion Kinematic mount, this isn't new technology. This has been around forever, but in precision machine designing circles and optical systems and stuff of that nature that requires it's really sensitive to distortion and repeatability, like the whole field of precision engineering. I have a background in that. My first job out of college was with designing linear stages in chasing nanometer repeatability, so I was exposed to these kind of concerns early on in my career. So this is kind of like it's like distilled down from all the white papers, isn't it? And it's presented as like a working man's copy of this that's readily applicable. And what it boils down to, and I would encourage you to read through the everything up here if you have the interest to do it. It's there's some really great articles. But what it boils down to is basically 3 ball bearings located in 3 V grooves, providing a total of 6 points of contact for the system. And the reason for that is that's all you need to perfectly constrain a kinematic system. without over constraining it. So if you add more points of contact, if you're, there's, it's almost impossible to predict how many actual contact points you have between two surfaces instead of just points. Unless you're lapping everything in or grinding it really well, like inevitably there's going to be high spots that are, imperfections that are going to influence your results. And this isn't, this particular application probably isn't that critical, but it's just a design exercise. I want to try to make it the best I can, and with the knowledge I have, and that's what I went with here. But let's look at the design of the mechanism. So it's really simple. There's 3 ball bearings that are press fit into the upper half of the mount, which protrude enough from this pocket to contact mating grooves in that are machined into the base plate. So these are 60-degree grooves, and we'll discuss a little bit about that once we get into some section views. So once you perfectly constrain it in X and Y as well as rotation, the only thing you're left to contend with is vertical displacement, which is what the magnets are for. They provide the preload for the mechanism, the attractive force, to keep the ball bearings in contact with these grooves, to keep it from, rolling in either direction, and kind of influencing the stylus position. Because if you think of, with how far away this stylus is from the center of this joint, if there isn't enough preload or there's more compliance than what is ideal, it's going to be magnified up here, right? And this is what we care about. We want this to be accurate. When you take it off and put it back on, we want it to come back in the same position, probably within a tenth or two if possible. So that's the mechanism. If we look at some section views, let me rotate this. So this is a shot of the ball. This is a cross section of the ball bearing in its mating V groove. I went with and there's a bunch of other discussion about this in the articles on practical precision. There's a bunch of discussion on ramp angle. Basically, the shallower the angle, the easier it is to install and remove, but the lower the moment resistance is for the upper half kind of climbing out of the pocket. And it becomes more important if you have stresses involved. So you can design the center of this mounting pattern in a few ways, right? If it's a static system and it's not moving, not really experiencing any kind of forces, it makes sense to do it about the center of mass, which is kind of what I did here. I didn't do any great analysis. I just kind of picked a stock size of material that I wanted to work from and that would fit my needs for where it wanted to live on the table. And I tried to maximize the footprint within those constraints. In this case, it's 2 5/8 diameter 4140 round stock that I'm machining this from. If it's something that's under load, or even if you get more complicated from that, if you have like thermal gradients you have to deal with, it probably makes more sense to design the center of this mechanism around the center of stiffness, which is roughly approximated by the second moment of inertia of your system. Or if it's thermal, try to figure out where the center of expansion is. So it's kind of situation dependent, but this is a relatively simple application, so I tried to keep the design simple. But back to the ramp angle that I chose. So I went with 60 degrees, mainly because as you increase this ramp angle, think of it as climbing up a hill. If you have forces applied that are would want to roll this upper half off of the base plate, in one direction or another. Not that we do. It would be a lot harder for the ball to roll out on a steep surface than it would be a shallower one. It's like climbing a hill. You know, shallower grades are a lot easier to walk up. Same principle. The other thing I liked about this was, and I don't have any calculations to back this up, it just made my brain feel fuzzy and warm. The center of the ball, of the component that's defining the position for this entire system, is a lot closer to the center of this joint. So if you draw a line between the points of contact on this ball bearing and strike your center line, the center of the actual ball bearing is a lot closer to that than it would be if you had a 45-degree groove and this thing was sitting up a lot higher. So that gave me the warm and fuzzies. I don't know if it actually means anything, but that's what I went with. Design point 2, which you can also see here. So all this stuff is housed in a pocket on the underside of the mount, right? And when you made it down, if you have this on the table, you want to be able to shield it from chips and coolant getting in here, because if you're cutting anything magnetic, inevitably it's going to wind up on your magnets, which is going to negatively impact the the repeatability or like the dependability of this thing. You don't want to have to take great care to keep this thing clean, or even worse, do cleaning activities every time you want to put it back on. I mean, you should inspect it at least, but you don't want to have to do a bunch of rework. If you can design your way out of a situation, it's often much better than having to remediate it with a bunch of processes after it's already happened, right? So that was the idea behind incorporating this labyrinth seal. So finally, the third consideration was overall height, and it's this might look a little tall, but let me bring up my table configuration, and this is what we're working with. The X7 table. Kind of my default setup, I'll probably have two 6-inch vices on here mounted to a subplate, op 1 for roughing in one vise, and then soft jaws to finish a part off in op 2, just to try and make me a little bit more efficient instead of have to reorient everything twice the number of times. So my plan is to mount these vices to their own subplate, which is kind of functions as a poor man's 0-point system. It's a 3-position subplate, and the vices I have, these are from Glacier Machine Tools. They're pre-drilled on the bottom with a 96mm square pattern for use with like a 5th axis style pull stud. So I can install my own my own studs, my own locating studs, right, to screw in, and then instead of having the clamp screw, I'll just utilize the bolts on top to bolt them in place. So I didn't see a whole bunch of the difference between undoing 2 screws versus 1 wasn't worth spending thousands of dollars on, at least not at the point where I'm at here, just getting started. But back to the tool setter. So this thing obviously needs to live within the machining volume of the machine. Yeah, it's kind of a stupid phrase. This translucent box represents my machining volume. So left edge is my X negative limit, the right hand edge is the X plus limit. So this stylus obviously needs to live in here somewhere. This allows me to perform recalibrations if I need to, which is probably good preventative maintenance. If if this location drifts even a couple thousandths, it's going to have an influence on your tool measurements. And if the part tolerances that you're trying to achieve demand it, that might be the difference. And you want this thing to be as accurate as it can be. just to try to remove error from your system and from your processes. That isn't really necessary if you pay attention to it, right? The other consideration, well, I guess the final consideration is height. So I positioned the stylus above the fixed jaw of the vise. Calibration was one aspect of this. The other aspect is if I have to touch off a face mill or something larger in diameter, I need clearance in order to do that because it's not centered on the stylus when you touch those off. So I have this whole area here available for that purpose. And if we take a look at an end view, where I'm drawing my mouse is kind of, this is a conventional vise, so this fixed jaw never moves. Where I'm drawing my cursor here, that's kind of going to be my, my maximum threshold for where the material is going to impede on the tool setter when it lives on the machine. So in theory, I think this placement is going to work out good for like a lot of different setups. Most of the tools I use are 3 inches or longer, so this also gives me greater spindle clearance, between the nose of my spindle and the top of my vise or any work that I have clamped up in here. So I don't have to worry if I break a tool, I can put the tool setter back on and not have to tear my setup down or like do a bunch of stupid stuff to try to like retouch off my tool. Kind of defeats the purpose of having a tool setter if it's difficult or inconvenient to use. And this kind of dovetails into a broader conversation on what I'm trying to do, right? I don't have at this point I'm just starting out, I'm doing job shop work, or at least trying to. I don't have a niche yet. So I need to be adaptable, and while I'm doing that, I'm doing my own product design in the background, which that requires some incubation to flesh that out. So in the meantime, I'm doing job shop work, and there's a ton of really valuable lessons to learn by doing that, even if it isn't the most glamorous, it's or the most lucrative. Especially somebody new starting out, such as myself, there's from programming, from tool selection, from fixturing, from there's a million different things to learn, and there's a new challenge every time. So if you get good at that, it's really strengthens your creativity and your problem solving and your efficiency as well, right? So that's I think that's really valuable to do, and that's what I'm trying to work through with this. It's why I want it to be as adaptable as I can. I got my 2 vices here, which are going to be kind of like my default setup. I have the 4th axis. This is mounted to a Pearson Smart plate. I got this 0-point plate on here. Say I have a something that's I do my op 1 in a vise, and I need to do op 2 in the 4th axis. I can do it. So I remove the 1 vise, leave this here, and then I have all this machining volume available to rotate the 4th and spin the part. Or I could remove them both and put a tombstone in. But either way, like this tool setter position, I need to work through it and prove this out. But I'm thinking, I've spent a bunch of hours in Fusion thinking about this stuff and trying to analyze it. It looks like it'll work for a lot of different use cases. So that's kind of why I designed it this way. I guess that's enough yapping, enough Fusion. We can go look at the actual tool setter and do some repeatability testing, and maybe some of the other challenges that I experienced with through the process of like trying to get this thing to work. So let's go do that.